Welcome to the Crazy Hat Chemist. So another video here on kinetics. So let's get moving. Bam! So today we're talking about a kinetics calculation number 1. All right. So sugar fermentation occurs according to the following rate law. So R is equal to K, sugar concentration, to the first exponent there. So what is the order of this reaction? I think you got it. It is a first order rate law, okay? And the associated rate constant of the following, and this is given, that's K is equal to 3.3 times 10 to the negative 4 per second, okay? So what is the half-life of this reaction? That's the question that we need to answer here. Okay, from the rate law, you can see the rate law, it is to the first power. Okay, this is a first order reaction with first order kinetics must be used in this. Okay, that is the mathematical equations associated with first order reactions must be used with this. Okay, additionally, the rate constant is in per units of time. So it's per second, per minute, per hour, per day, per year, which corresponds to first order rate kinetics as well. So hopefully you got those two things tied together. You need to look at that lecture that I had on summary of rate laws of 0, first, and second order. Relook at that slide, that whole section of that lecture, and that's so very important for all of these kinetics problems. So this is the integrated rate law. That's natural log of x of t divided by x of naught is equal to negative kt. You need to memorize that, have that stuck in your brain there. We're going to be using that a lot. Okay, so we're going to solve for the half-life equation for the first order reaction. Now on the previous lecture, I solved for the half-life equation, that's t sub 1/2, okay, for 0 and second order, and I showed that those were dependent on the initial concentration, and I alluded to that that is not the case with first order. So here is first order solved for you. So when t is equal to t of 1/2, that is natural log, I've plugged this into the integrated first order rate law. So hopefully this makes sense for you. So natural log of 1 and over 2, right? Because if the initial concentration is 2, then half of that would be 1. You could have plugged in any numbers in here. That is the initial concentration, that is t of 0 is, let's say, 100%. Then at half of it, then you would have 50% at x of t. All right, so hopefully that makes sense. So natural log of 1 over 2 is equal to negative kt to the 1/2. So t to the 1/2 there, that is the half-life. Okay, now what we've done is we've used our rules of natural logarithms here and turned this division problem into a subtraction problem. So that's natural log of 1 minus natural log of 2 is equal to negative kt of 1/2. Now I want you to ask yourself the question, what is the natural log of 1? Okay, that's very important that you know that. If you don't know it, pull out your calculator right now and find the natural log of 1. It's a very special number. Okay, and that number is 0. So natural log of 1 is 0. So that left-hand side there, the natural log of 1 is a 0. Then it's minus natural log of 2 is equal to negative kt of 1/2. Now we're going to solve for t of 1/2. So therefore we're going to divide both sides by negative k. Negative k, not negative key, negative k. All right, and now we have t of 1/2 is equal to negative ln, natural log of 2, divided by negative k. And so now we're going to get rid of those negative signs, and what do we got? Right there in the upper right-hand corner there in the blue, t of 1/2 is equal to natural log of 2 over k. I have just solved for the half-life equation for the integrated first-order rate law, or the half-life equation for first-order kinetics. I did that for 0 order and second order on the previous lecture, but this one is so very important because this is used so much. Okay, so now that we know this information, that is, we know the integrated rate law and we know the half-life equation for first order kinetics, now we can actually solve this problem at hand. Because what are we looking for is what is the half-life for this reaction. So t of 1/2 is equal to natural log of 2 over k. We know that. natural log of 2 is equal to a number. K is given in this problem at 3.3 times 10 to the negative 4 per second. So we're going to plug that number into the half-life equation. So natural log of 2 is a number, like I said, and then we got the K, the rate constant, plugged in there. Okay, and then we solve for that, and t of 1/2 is equal to 2100 seconds. I do have two significant figures there because my rate constant had two significant figures. So notice that the half-life is in time, and that's why it's seconds. Okay, that is an awesome, really great problem there, especially solving for the half-life itself. Okay, I am the Crazy Hat Chemist, and I hope you have a great Thanksgiving, or you like turkey, or you think yourself of a turkey. Okay, have a great day. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Find me on the web and find my website. On my website has all my videos. Subscribe to my YouTube channel, and I'm going to see you next time for more kinetics problems. Bye for now.